The topic for discussion in this video lecture is about the navigation and path planning, and we are going to see very particularly about simultaneous localization and mapping, which is shortly called as SLAM. And this is Dr. S. Mohan Lakshmi, Professor and Head, Department of ECE from Rohini College of Engineering and Technology. On completion, the student will be able to explain SLAM. They will be able to explain the applications of SLAM, and even they will be able to represent the models of SLAM. So, in a nutshell, what is SLAM? It is a technique used to build up a map with an unknown environment or a known environment while at the same time keeping track of the current location. So, what is SLAM? So, computing the RoboSpose and the map of the environment at the same time. That's why it is called as a simultaneous localization and mapping. Localization is nothing but estimating the robo's location. Mapping is building a map. SLAM is making, that is locating the robo as well as building the map simultaneously. So here this is the example of localization for a mobile robo. So this will estimate the robo's poses given the landmarks. So the robo will know the map. Robo knows landmarks on the map, and it will see the landmark and it will want to estimate its pose. So here the yellow stars means that it has a fixed firm information, and these are the round circle which will tell you about the predicted state. Example of mapping. So here robo is will create the map. It will estimate the landmarks given the robo poses. So in this case it will not know the map or its path. So though it will know only its landmark, it will know only its pose, and it will estimate the landmarks in the map to create or update, or it will extend the map. An example of a SLAM. So here it will estimate the robo poses as well as the landmarks at the same time. So in the previous case we have seen either it goes for a mapping or it goes for a localization. But once you go for a SLAM, it will take both the things. So the robo does not know the map or its path, and here as usual it will estimate its pose, it will seize the landmark, it will estimate the landmarks on the map to create or update or extend the map. Here also you could see here the dotted line gives a real value, and the other one it gives a predicted value. And this is like a chicken or egg problem. So what we need first, either we need a map for localization or we need a post estimate for mapping. So this is like a chicken egg problem. So why this problem is very important? So this is considered a very fundamental problem, especially for the autonomous navigation, autonomous robots, and this forms the most basis for the most navigation system. So you cannot avoid it. So what are the applications of a SLAM? It is used in a central to a range of indoor, outdoor, in-air, underwater applications, both for manned and autonomous vehicles. So if I'm going to use in home, then it could be a vacuum cleaner or a lawn mower. If it is going to be used in air, it is a surveillance with unmanned air vehicles. Similarly, underwater, underground, space, terrain mapping for localization. So these are the applications where it is given from the as pictures: underground, space, undersea, indoors. So how do we define? So the robo's control will be given, which is specified as U1 is to T, and observation is specified as Z1 is to T. And what we wanted, map of the environment, which is defined as M, and what we really require is the path of the robo. So how it will take from x0 to t at these are the various points x0, x1, x2 till t, various times. So we go for probabilistic approaches. So uncertainty in the robo's motion and observation. Why we go for probabilistic approaches? The reason is the robo motion can be uncertain. and even the observation can be uncertain. So normally we go for probabilistic theory to explicitly represent the uncertainty. So you cannot say the robo is exactly here. So we go for a probability distribution like this, where you could say the robo is somewhere here. So in probabilistic terms, here you could see here the P represents a distribution, X naught is path, M is mapping, and this is given, and we need to have a observations and the controls, which is represented as with Z and U respectively. So this represents a graphical model. So we have the path unknown, we have the controls which is observed, observations observed, and this is the map. So you can see here P x no x0 to t with the map, with the observations and the controls. So we have two types of SLAM, which is called as a full SLAM as well as the online SLAM. Full SLAM is nothing but it will estimate the entire path, and online SLAM will seek or it will estimate only the most recent pose. And you could see in the probability distribution, in the first case it is given as x naught is to capital T, which will take the entire path, whereas in the second case you could see pxt, which represents only the current pose. So this is the graphical model of full SLAM and online SLAM. Obviously, we know that for the full SLAM, it is like from the 0th position to the t, the entire path till it takes the entire path. Whereas here you go with for from one pose to the next pose at a particular point of the path. So online SLAM means modularizing out the previous poses. So normally we use integrations, or they are used typically one at a time. So this is represents a graphical model of online SLAM. So where it is represented from x naught t plus x naught to t plus 1. Similarly, when I take for the controls and observation, you need to take the t plus 1 is for z as well as for the u. Why SLAM problem is so hard to solve? So we don't know the path, we don't know the map, so it is both unknown for the robo, and most of the map and the post estimates are correlated, and the mapping between observations and the map is unknown, and picking wrong data associations can have very divergence catastrophic consequences. Thank you.